In our, in our last video, we looked at finding all of the zeros and completely factoring a polynomial if we were given one of the zeros to get started with. And we saw that we could, if we started out, say, with a cubic polynomial, we could factor out one factor based on the zero that we were given, and then we were left with the quadratic. And then we could use quadratic methods to find the other two zeros, and then backtrack and find the other two factors. In this video, we're going to look at what do we do if we have a polynomial, but we are not given any possible zeros. We're not given a zero to start with. We're going to have to come up with a list of possible zeros to see if any of them are zeros. And then once we can factor out one factor, we get to a quadratic, and we can use quadratic methods. So we're going to use something called the rational zero theorem. And remember, a rational number is a number that can be written as a fraction. So numbers like 2/3, -8, 1 are rational numbers. Numbers like the square root of 2, -3i, are not rational numbers. It actually turns out that the square root of 2 is irrational. It is still a real number, so it will show up on the real number line. And -3i is imaginary. And I can easily see that that's an imaginary number because it has that I in it. Remember, I is the square root of -1. So what we need to do when we're given a polynomial is come up with a list of numbers that could be zeros of that polynomial if that polynomial has any rational zeros. Let's backtrack a minute. Let's think about if we have a function 3x plus 5 times 2x minus 7. I'd like you to actually FOIL this out and find out what this function looks like. So pause the video, FOIL this, and write what the function is. All right, we see we have 3x times 2x is 6x squared minus 21x plus 10x minus 35. So f of x is equal to 6x squared minus 11x minus 35. Okay, so if we were to be finding the zeros of this function, we would work it the other way around. We would set the function equal to 0. We would factor it. And obviously it's going to be those two factors because that's what we multiplied together to get that function. And then I'd like you to go ahead and do the last step. I'd like you to set each of the factors equal to 0 and solve for x. Pause the video and do that. All right, we see we have 3x plus 5 equals 0. Subtract the 5 and divide by 3. And actually I want to write it like this. Okay, and then we do the same thing with the other factor. Add the 7 and divide by 2. Now I want you to notice some patterns here. Notice that when I multiply this term, or this coefficient times this, I get the 6x here. I get the 6. 3 times 2 is 6. when I multiply the 5 and the -7, I get the -35. So the first two numbers here multiply to give me my first number here. My last numbers here and here multiply to give me my last number here. And if I had more factors, that would continue on. I would multiply this first number, the coefficient of x, in every single factor to get this first number. And I would multiply every one of my constants here and here and here all the way along to get my last number. And we saw that when we were looking at finding our y-intercepts. But notice what happens when we solve and get our zeros. Notice that every one of our numerators here come from multiplying together to get 35. So all of the numerators are factors of the constant. They're literally what you multiply together to get the constant. And notice that my denominators here in my zeros are the 3 and the 2, which were here and here. And multiply, taking all of them and multiplying together, I get this number. So we're going to have that the denominators would be factors of, and we're going to call that first number, that coefficient of the highest term, the initial coefficient. So what we've seen is that if we were working backwards, if we knew all of our zeros, all of the denominators multiplied together would give me, excuse me, the initial coefficient, and all of the numerators multiplied together would give me the constant. But we're going the other way. We're going the other direction. If we're given a polynomial, then we know that the only way we could end up with a 6 here and a 35 here is if we had rational coefficients. The only possible rational coefficients, the only possible rational zeros of that polynomial. And this is what's called the rational zero theorem. I couldn't end up with a zero that, say, had a 7 in the denominator unless the number at the very beginning of the polynomial had a 7 as a factor. So how does this help us get started? Let's say that we are given a polynomial. P of x equals 2x cubed plus 7x squared minus 7x minus 30. Now this one will not factor using grouping. If I tried to pull out the largest common term from the first two or the largest common factor from the second two, I'm not going to end up with the same thing left to divide out. So I cannot use factoring by grouping. But I wanted to find all zeros and completely factor this polynomial. I don't have a zero given to me to get started with the synthetic division, but I can use the possible rational zero theorem to find out some numbers that could be rational zeros. And then I can start with that list and start doing my synthetic division. So to list my possible rational zeros. And all of these are not going to be zeros. These are only the ones that could work. If this polynomial has rational zeros, they have to be on this list. And to do that, I'm going to list the factors of the constant. In this case, my constant is negative 30. So I think about what are all the different things that could multiply to give me 30. I could multiply 1 and 30. I could multiply 2 and 15. I could multiply 3 and 10. And I could multiply 5 and 6. Now notice that I didn't put plus and minus, because when we have three factors, which we will because it's x cubed, I don't know if it's plus, plus, minus, 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 minus. So I'm just going to put a big giant plus or minus out here, and I'll explain what that means in a minute. And this is going to be over all of the possible factors of the initial coefficient, which is 2. So the only 2 that I have there are 1 times 2. So this list really means every single one of my numerators over every single one of my denominators, and I could have the positive one or the negative one. So I could have 1 over 1, 2 over 1, 3 over 1, etc. Every single one of those numerators over 1. Also, the negative version of every one of those. And then I could have every one of my numerators over 2. So 1 over 2. 2 over 2, which is already 1, is already there. 3 over 2. 5 over 2. 6 over 2, which is 3, it's already there. 10 over 2, which is 5, it's already there. 15 over 2, and 30 over 2, which is 15, it's already there. And then the negative version of every one of these. So what the possible rational zeros theorem says is that if this polynomial has rational zeros, they must be one of these listed numbers. This way of writing it is a shorthand way of writing it, and it's perfectly fine if you just write it that way, but it's important that you understand that it really includes all of these numbers. Okay, now what I'm going to do is I'm going to say, okay, this is a lot of numbers here. This is a long list. But I need to find which of these numbers on the list is a 0 so I can factor the factor that goes with it and get down to a quadratic. I'm not going to start with negative 15 halves or with negative 30 or one of those a little bit more difficult numbers. I'm just going to start at the beginning of my list, and I'm going to work my way through the list. For instance, I'm going to try 1. Does 1, if I do synthetic division with my original polynomial here, do I get 1 as, or do I get 0 as my remainder? That means that 1 is a 0. If that one doesn't work, I'm going to try negative 1 and so on. And I'm just going to work my way through the list here until I get to a 0, a number that is actually a 0. So I want you to go ahead and start working your way through the list. Do the first couple of numbers, and I'm going to give you a hint here. You are going to find a 0 fairly early on in the list here, so just start and work with those numbers, and hopefully you'll come up with a 0 before you get too far. Pause the video, start doing your synthetic division, and stop when you get to a number that gives you a 0 remainder, which means that that number is a 0 of the polynomial, and then turn the video back on. Okay, so 2 drops down, 1 times 2, and I just multiply and add all the way across. And I see that's negative 18. That is not equal to 0, so I know 1 is not a 0. So I just go back to the beginning and try the next one. And again, not a 0. So I try the next one. And then I see that I get a 0 remainder here. So that means 2 is a 0 of f of x. 2 is a 0 of f of x. So now I can continue on finding the other 2 zeros. So what I just did here is I divided out the factor that went with positive 2 is a 0, and I was left with a quadratic quotient. So I want you to see if you can write the factor that I just divided out with that synthetic division and the quadratic quotient that was left from the synthetic division. Pause the video, write that, and then start the video again. So if positive 2 is a 0, that means x minus 2 is a factor. And the other factor, the other quadratic factor here is 2x squared plus 11x plus 15. And we learned how to do this in our first video on synthetic division. So review that if you need to. So now we need to solve this quadratic. We need to solve 2x squared plus 11x plus 15 equals 0 for x to find our other 2 zeros. And if we remember our quadratic method, we do have an x term, so we need it in standard form, keeping the x squared term positive, which it is. We need to look for any common numbers to divide out. There are not any. We need to look for any common variables to divide out. There are not any. And then we need to try to factor. So we're going to have a factorization here. And we know we're going to have 2x and x because we have 2x squared. So we can use the AC method, or we can use the factoring by guess and check method to figure out what numbers need to go here and here so that we get 15 when we multiply those two, and we get 11 when we multiply our outer and inner terms and add them together. So pause the video, use whatever method works for you, finish the factorization, and then solve each factor to get our last 2 zeros, and then turn the video back on. All right, so I used guess and check, and I came up with 2x plus 5 and x plus 3, because if I check over here, this is going to be my check. I'm going to move it way down here. 2x plus 5, x plus 3. I knew I had to have 2x and x to get 2x squared. I knew I had to have factors of 15, two things that multiplied to give me 15 here and here. And if I multiply my outer and my inner, I get 6x plus 5x equals 11x, which is my correct middle term. So this is my correct factorization. Then I set each factor equal to 0 and solve for x. And those are my last 2 zeros. So if I list my zeros, it turned out in this one that all of my zeros were rational numbers. 2, -5/2, and -3. And notice if I look back at my possible rational zeros list, there's the 2, there's the -5/2, and here is the -3. And all of those numbers were indeed on my possible rational zero list. But if I look back at what I wanted to do here, I wanted to find all of the zeros, and I also wanted to completely factor. I did that completely factor step as I was solving here. So my factors, the things I would multiply together to get that polynomial, would be x minus 2. And then looking back at my factorization here, I have 2x plus 5, which gave me the -5/2, and x plus 3, which gave me the -3. And I have completed the problem. All right, let's look at another example here. Let's say I want to do the same thing. I want to find all of the zeros of the polynomial f of x equals x cubed plus 3x squared plus 7x plus 5. And if I glance at that really quickly, I think, can I use factoring by grouping? If I pull out an x squared, I'm left with x plus 3. And then on the second two, I'm left with 7x plus 5. That doesn't match, so I cannot use factoring by grouping. So I'm going to have to use the possible rational zero theorem and synthetic division. So I want you to see if you can list the possible rational zeros. And remember, that is that plus or minus, and then the ratio of the factors of 5 over the factors of this understood 1. See if you can list the possible rational zeros here. All right, the factors of 5, 1 and 5. The only way I can get a 5. Factors of 1, just 1. So my list here is just 1, -1, 5, and -5. If this polynomial has a rational zero, a zero that can be written as a fraction, not with the square root in it, not with an I in it, it has to be one of these 4 numbers. So I want you to go ahead and do your synthetic division, find which of these numbers is a rational zero, and then write your polynomial as that factor factored out and the remaining quadratic. And then we'll start from there again. All right, I'm just going to start with 1. Start with the easiest one here. And I have cubed, squared, x constant, so I'm not missing any coefficients. Be sure to watch for that. Drop the 1 down. And add. And 16. So that is not a 0. So I try the next one. I'm just going to do -1. I could have done 5 and then go to the -1, whichever, however I want to do this. And I see that, yes, I do get a 0, so that tells me -1 is a 0 of f of x. And what I just did was I factored out the factor that goes with -1 is x plus 1, and I was left with x squared plus 2x plus 5. So now I need to solve the quadratic equation, x squared plus 2x plus 5 equals 0 to get my other two zeros. So if I try to factor this, I'm going to try to factor this first. Actually, what I'm going to do is I'm going to say I have my bx term. If I did not, I would isolate x squared plus or minus square root, but I do have my bx term. So I get it equal to 0, keeping x squared positive. Look for common numbers, there are not any. Look for common variables, there are not any. Try to factor. So the only way I could get x squared and positive 5 here and here is x plus 1 and x plus 5. And if I try to factor that back out, FOIL that back out, I get x squared plus 6x plus 5. Not the correct middle term. So this one does not factor. If it does not factor, we use the quadratic formula. So I want you to list what A is, what B is, what C is. I want you to write the quadratic formula, pause the video, plug the numbers in, simplify to get the last two zeros. So A is 1, B is 2, C is 5. The quadratic formula from memory, negative B plus or minus square root of B squared minus 4 times A times C all over 2 times A. So I have negative 2 plus or minus 2 squared minus 4 times 1 times 5 all over 2 times 1. 4 times 1 times 5 is 20 over 2. Square root of 4 minus 20 is negative 16. All right, when I have this negative under the square root, that tells me I have an I, an imaginary number. So I know I have an I here. And the square root of 16 is a perfect square, is 4. And this 2 cancels this 2 and the 4. So negative 2 over 2 is negative 1. 4i over 2 is 2i. So be careful here that this 2 cancels the 2 here and the 4 here. If it won't cancel both, you can't cancel. So I have determined that my zeros, my 3 zeros, because I had a cubic, were the one I started with here, the negative 1. Was my only rational 0, and then I have negative 1 plus 2i and negative 1 minus 2i were 2 complex or imaginary zeros, and I have completely found all 3 of my zeros. In our next video, we're going to look at what if I'm given the zeros and I need to go back and figure out what was